So once again, welcome everyone to this new webinar. We'll start now and probably someone else will join in a few minutes. So today's webinar is about seismic isolation using friction pendulums. Let me share my screen. Here we are. So before starting with the webinar, I want to tell you that tomorrow we will release the new version of STKO, version 2. And in this webinar, I will be using this new version. There are many new features. Well, the first one is about the licensing system. As you know, STKO is not free. There is a trial version, then there are research and commercial version. But starting from tomorrow, so with version 2, there will also a free license for people doing just personal use of STKO with just some small limitation, but the program, all the features of the program are available. So it will be useful for people that cannot afford the license. So by tomorrow, you will be able to download STKO from our website, and you will be able to access the files that I will use today that of course need version 2 of STKO. And also we added some new features inside OpenSees, for example, like the modal properties or the response spectrum analysis, basically the ones that I've shown in the previous webinar. They have been accepted by the OpenSees maintainers, so now they are in the OpenSees source code. It is not yet compiled, but if you want, you can download the precompiled version by Professor Tarke. You can find information on our website, because his version, he has compiled the new version of OpenSees, okay? So you can find all the new features there. And there is basically OpenSees sequential and the two parallel OpenSees version, OpenSees MP, and now there is also OpenSees SP. Okay, so what about the new features of STKO2? Well, there are some minor bug fixes, but tomorrow when you will download the software, you will see all the changelog, but there are some minor bug fixes, some improvements. The most important one is that now we have a scripting framework. With the scripting framework, now you can interact with STKO using a Python API. It means that well before, the Python scripts were only available to define new components. Okay, now you can actually have a small editor here, like for example, like a MATLAB editor, where you have your script explorer, you have your folders with your own Python scripts, and then you have your script editor here, where you can create new files, you can modify them, you can save them, and then you can run them. Through these files here, you can directly access the current STKO document, both in the preprocessor and in the postprocessor, okay? So for example, here, this is how you have it now. You can switch on the script environment, okay? So that now you have the new script environment here. There will be also the documentation for this one. Since the scripting is quite, it's a very large topic, basically all our new webinars will be about scripting, okay? So our future webinar will explain you step by step how to use these new features. Now, just to give you an idea of what you can do, actually I just gave you a small preview in the previous webinar when I was talking about response spectrum. I've shown you how you can use the scripting environment in the postprocessor to combine results, for example, to do the modal combination for response spectrum analysis. But you can do much more than that. For example, here there is a small example on how to manipulate the mesh. Now imagine you have a model with a quite fine mesh like this one, and you want to assign random material parameter, okay? Now this is not the topic of today's webinar, but just to show you how you can interact with it. So here there is a small Python script where I was trying to implement a Gaussian random field, spatially correlated Gaussian random field, to assign material heterogeneities here. Now the nice thing about this one is that now you can write your Python file here, you can access the application, you can access the document, you can access everything. For example, I can get the mesh of the document, I can get the mesh of every single geometry, I can create new materials, a new visual representation, and I can do whatever I want. In this case, I was creating a random field, and I was assigning this random field onto the mesh in such a way that I can use it to create random material parameters. Just to give you an example, I run this script, and here I just created a well, the same version of this model to have a preview, just translate it, and I just said, okay, I want, for example, the young modulus to be between 30, which is the mean value, and then with a certain standard deviation. And then basically this script allows you to assign a different material parameter to each and every element using some spatial correlation. This is one of the many things you can do with the Python scripting environment. And I will show you how to use the Python scripting environment also in today's webinar, and how to post-process the results of a time history analysis. Okay, so now let me go back here and let's start with a new blank project. Okay, so tomorrow you will have access to the contents of today's webinar. Here you have some data, some reference, an Excel file where you can calibrate material parameters for the single and double friction pendulums. Then you also have some reference here, and then you have the webinar Friction Pendulum, which is the folder where you have the file that we are going to use today. And there is also a small Python script that I will use to explain how you can post-process some of the data we extract from this file. Okay, so you can start by opening the file provided here. So building single friction. And this one is basically very similar to the same model we used in our previous webinar about seismic isolation. But last time we've been using elastomeric bearings. Okay, now we have the same model. I just made it slightly smaller but in this case we will be using friction pendulums. Okay, so everything is ready here. I don't want to waste time doing the model again. I will just explain you what I have in my model here. Okay, so let me just switch off the grid. I don't need it. Okay, so we have our structure here is pretty regular. Okay, it has okay, so what do we have here? Well, first thing we have is a local axis that has been assigned to the isolation system down here to give a local orientation. Then I will go back to the selection set later on. We have two geometries, okay? The first geometry here is the assembly of my structure. So it has both the frame, which is this one basically. Let me select it, okay? It is everything, so basically the base floor made with shells, and then we have all the frames and also all the master nodes here in the middle for the rigid diaphragm, okay? So this one is the first geometry. And then we have a second geometry, which is basically this group of nodes here at the bottom. They are, of course, detached from the structure because then we will attach them by means of interactions, okay? And they will be our isolation system. So we have just two geometries and we have two interactions. One is for the rigid diaphragm, okay? So let me select this one. And you know already how to do a rigid diaphragm. You just need to select all the master nodes in the middle as master, and then all the other nodes of every floor as slaves, okay? And this one will be used to create the rigid diaphragm multi-point constraint. Then we have another interaction down here, which is used for the isolation system, okay? Now, when you create this interaction, it is important that you select, let me show you. It is important that you select the base nodes. Oh, let me go into the front view. Okay, so the base nodes here will be the master nodes, and the top nodes will be the slave nodes, in such a way that the local z-axis of the zero-length element used for the isolation system will point towards the global z. Okay, so you can just create an interaction. You select the base node as masters, and the top nodes are slaves. Okay, so now you have your geometry and your two interactions. Then here I created some selection sets because they are useful for selections of the different components. I created a selection set for columns, okay, then a selection set for all the beams, then we have a selection set for the slab, and then we have a selection set for the base nodes. I need them because I will create a monitor to monitor the base reaction, so I need to create a selection set for the base nodes. Then I also have a selection set for the topmost node here on the top floor, because I want to monitor the global displacement of my structure. And then I also need the top nodes of the isolator, okay? I will show you later on why I need them, but I need to apply some extra boundary condition there. Then we have the selection set for the master nodes here. This is not necessary, but it is used only for if you need to extract some data at the master nodes. And then I have a selection set for the isolators. Okay? So up to here we have all our geometry. Okay, so geometries, interaction, and all the selection sets that we need. Okay, now we can collapse them. And now we can move to the definitions. Okay, so the definition, we have a standard linear time series for the application of the vertical loads. Okay, so just a ramp that goes from 0 to 1 in the first gravity, and it will be used for the application of vertical loads in the first gravity analysis. Okay, then we will perform a time history analysis, so we need an accelerogram for both x and y directions. Now in this case we were using the Coulomb accelerogram. It is about 40 seconds. Okay. Now for the sake of this webinar, I will be analyzing only 15 seconds because actually it is here the most important part of our acceleration. But if you want, you can just go into the analysis and set 40 seconds as the last one. And the time step is 0.01 seconds. So this one is the acceleration in x, and this one is the acceleration in y. Okay, now last time I've been using the elastomeric bearings. Now in this case we will be using the friction pendulum. In this first example I will show you the single friction pendulum. Then in a future webinar we will be using the triple friction pendulum. But the main difference between them and the elastomeric bearings is that now they need a friction model. So a way for them to understand how the shear force depends on the normal force. Okay, there are many possibilities in OpenSees, and now here I have implemented 4 of them. But in this example, I will use the simplest one, so the Coulomb one. And the Coulomb here. So whenever you want to create a friction model, it is under definition. So you go under model, friction models, and you choose one of them. Now in this case, I was using a Coulomb. So as you know, the more Coulomb law is just a linear relationship between the shear force and the normal force, meaning that the friction coefficient is constant. Okay, so if you go here on the website and you see the graph between friction coefficient and the velocity here is constant. Okay, but then of course you can play also with the others to see the differences. Okay. Okay, so once you have the friction model, you go on the physical properties. Okay, now in the physical properties, my entire structure is, just for the sake of simplicity, everything is elastic, and it has the same section both for columns and beams. Okay, so you have an elastic section for beams, for columns, sorry, another elastic section for all the beams. Then you have a slab here, a slab section. Once again, also here it is elastic. We don't need to put nonlinearity into our model now, as I will focus on the isolation system. Now, before creating the friction pendulum, because the friction pendulum is just an element, it does not need a material model. Okay, it needs some of these definitions here later on when I will use the element property. Okay, so once I define all my sections for beams and slabs, I need 2 uniaxial materials. One that will be used for the vertical component of the elastomeric of the friction pendulum, and the other one that will be used for the bending components. Okay. Now in my case, I don't want any stiffness on bending, so I just create a uniaxial material with a 0 Young modulus. Okay. While for the vertical component, I want an elastic no tension. Elastic no tension means that I have a quite stiff model here that acts only in compression and nothing in tension. So for example, if I test this one and I push it cyclic symmetric, okay, so you will see that in tension it gives no strength, only in compression. Okay, so this one will be used for the vertical component of the isolation system. Okay, so once you have those physical properties, you can move to the element properties. And here we have a beam element to be used for both beams and columns. Okay, so a simple elastic beam column elements. Then we have a shell element here for the slab. Linear kinematics, we don't want to include geometric nonlinearities. Then in the previous webinars, this one was the isolation system I was using. It was the elastomeric X. But I kept it here just for to do a comparison, but this one is not used now. What I'm using now instead is this one. So if I click select, you will see that it has been assigned to the interaction for the isolators. And let's see how it looks like. So you can go on edit and you can see the components of the friction pendulums. Okay. So the first thing that you have to set is the number of dimension. It can be 3D or 2D. Now in this case we are doing a 3D analysis, so 3D. Then here you need a tag associated with the previously defined friction model. Okay. Now you can choose one of them. In this case I'm using the Coulomb friction. But as I said, I defined 4 kinds of friction models. If you want to understand how they work, you can just change it and run the analysis to see what's the difference. RF is the effective radius of the concave surface. Okay, so this one is basically given by the catalog of the product that you use. Then you have an initial stiffness. Once again, this one can be found here in this Excel file. You can just put a reference normal load that you expect on that isolator, the radius, the friction coefficient, the expected displacement, and then all these other values are computed for you. Okay, so the initial stiffness, you can take this one and you can put it in the model. Here it has been put here with 2 order of magnitudes more, just to make it stiffer. Okay, then once you define the friction model, this friction model will act for the shear components. Okay, so in X and Y. But you still need to define something for the other degree of freedom. So for example, P is for the axial force in the Z direction. And as I told you, I'm using the friction vertical, which is this one, the uniaxial elastic no tension. While for torsion and the 2 bending moments, I'm using the material model 11, which is friction law, which is basically this one that has no stiffness. Okay, no stiffness in torsion and bending. There is only a compressive stiffness in the vertical model, in the vertical direction, and then in the 2 shear direction there is the friction model. Then you have some optional parameters that are not used here, just the number of iterations if you want to increase the tolerance or decrease the tolerance, or increase the number of iterations for the internal convergence of the friction pendulum element. Okay, once you have done that, you can simply drag and drop it onto the interaction for the friction pendulums. Okay, so this is fine. Now we can go to the boundary conditions. Okay, now in this case, when you're analyzing this base isolated system, the only fixity that you need is the fixity at the base nodes. Okay, so if I select this one, you will see that it has been assigned only to the bottom nodes. Okay, and this is fine. So all the degrees of freedom of the bottom nodes are fixed. Now here I also have another fix. Let me show you. It is applied, is also fixed on all the degrees of freedom, and it is applied to the fixed node, to the top nodes of the isolation system. This one will be used only to create a comparison between the fixed base and the isolated based systems, okay? So basically I will apply them at the beginning, both of them. I will do an eigenvalue analysis to see the vibration modes of the fixed based model. Then I will remove this condition here, and then we run an analysis on the base isolated model. Then, so these one are the only two single point constraints, so the only fixities that I have in my model. Then we have just one multi-point constraint, which is the rigid diaphragm, and as usual, you can edit it. You need to make sure that the perpendicular direction is the third direction, so the z-axis, and you need to apply them onto the interaction for the rigid diaphragm. And then the only other condition that you need are the nodal masses and nodal forces. Okay. Now this example is pretty simple. So basically you have the same size for all the spans here. So at most you have three kind of masses and loads. Okay, the one in the middle, the ones in the middle, the ones on the facade here, and the ones on the corner. That's why you have three pairs of nodal forces and masses on the central nodes, on the facade nodes, and on the corner nodes. Okay. Now, of course, in a real life structure, you will be many more combinations. But in this case, to make the model as easy as possible, I'm just using these three kind of mass and forces. Okay, so up to now you are ready with the boundary condition. You need to go to the analysis steps. Now there are quite a lot of analysis steps. I will explain you what I want to do in this kind of model. So the first thing that I do in all my models is to create a recorder, an MPCO recorder. Now for the sake of this webinar, I just need displacement, reaction forces, acceleration, because you may need to check the acceleration as well, and the mode of vibration. Okay, I don't want to focus on element results now because I don't need them. Okay, the modes of vibration are included just because I want to give you some keynotes about the eigenvalue analysis and what happens when you do eigenvalue analysis after a nonlinear analysis. Okay, there is quite some confusion about this topic, so I will try to give you an example. That's why I have modes of vibration here. Okay, so the second step is to apply boundary condition. As I said, my first aim here is to run an eigenvalue analysis of the fixed base model. Okay, so here in the boundary condition, I'm using both the fixity at the bottom node. Okay, so fixed base isolators, but I also include the fixity at the base of the structure. So in this way, including both of them, my structure is as a fixed base. Okay, it's not isolated at this point of the analysis. And then, of course, I have to include the multi-point constraint for rigid diaphragm. So here I have my fixed base model. Then I want to perform an eigenvalue analysis, and I want to extract modal properties. So if you remember in our previous webinar, I told you that when you run an eigenvalue analysis, you just say how many eigenvectors you want, but you cannot specify what kind of constraint handler you want, what kind of system of equation you want to use. So an easy way to define them is to create a fake analysis command before, that here I called setup eigeninitial. Okay, if you edit it, you can set up everything you want for an analysis. Just remember not to put anything here. So 0 time steps, which means basically I'm not doing an analysis. I'm just defining what are the components that are going to be used in the eigenvalue analysis. This is necessary because if you're doing a very large model and you do not specify those things here, OpenSees will not use a sparse solver like this one. It's going to use a dense solver. And then there is a problem. If your model is very large, that dense solver is not going to work. Okay? So the first thing that I do whenever I do an eigenvalue analysis is to set up all the components. Just remember to put 0 increment here, or a 0 duration, or both of them. It's not important, but at least one of them should be 0. And then do not forget to switch off the wipe analysis. Otherwise, this one will be useless, of course, because if you have wipe analysis, After the analysis, all these things will be removed. Okay, so no wipe analysis here. Okay, so once you have this command, you have set up all the components that OpenSees will use for the eigenvalue analysis. Okay, so after that, I set up an eigenvalue analysis, 6 eigenmodes, and I do not use any solver here because the default one is fine for me, which is the band RPAC. Okay, remember in many examples in OpenSees you see the full gen LAPAC. Full gen LAPAC is fine, but it's good only for small models because the full gen LAPAC works with dense matrices, okay, and tries to extract all the eigenvalues. So if your model is small, it is fine, but if your model is large, this is going to take forever, okay? So leave the default, just skip the default and you're fine. The default one will work with large models. Okay, so once we have the eigenvalue analysis, we can do the modal properties. As you know, the modal properties now are in OpenSees. In the previous webinar, I told you how to use this command using T-code, but in this case, in version 2 of STKO, we have included a custom command for that. So you can directly go here under analysis and you can find, in the previous version, you had only analysis command and eigen command. Now you also have modal properties and response spectrum, okay? So you choose modal properties, and here you have some of the, here you have the description. I want the print option because I want to print the results of the modal properties on my screen, but I also want to print it on a file, and this file will be called modal property initial. This one is not important, it's not going to change the results. Okay, here you have some documentation. So this one is fine. If you want to know something more about the modal properties, you can click here and it will open up a PDF with all the theory behind the computation of the modal properties, okay? And all the references that you need if you want to understand how it works. Okay, so this is fine. This one will print all the modal properties, remember, of the fixed base system. Once again, remember that an eigenvalue analysis does not record any result. Okay, so you have to explicitly tell OpenSees that you want to record the results of the eigenvalue analysis. So you can just create a custom command with the record command and the domain change just to tell that I'm going to start a new analysis later on. Okay. So up to here we are fine. We just completed the modal properties of the fixed base model. Now from here on, we want to analyze the base isolated model. So how can we do that? We can just remove the single point constraints, so the fixity that we applied on the slab. Okay, so once we remove that, our structure will be released here and the isolation system will be active. And this one can be done very easily. If you know, when you want to apply a condition, you go under pattern, you click on add pattern. When you want to remove it, it's basically the same thing. You go under pattern, but you go on the remove pattern, okay? And you can remove a load pattern, a single point constraint pattern, or a multi-point constraint pattern. Now in this case, I wanted to remove a single point constraint, and here you can select all the single points constraints that you want to remove. Now in my case, I just want to remove the fixities at the base of the structure, okay? In such a way that my isolation system becomes active. Okay, so after this step, the constraints that were here will be removed. Fine, so after this we can apply the vertical loads. When we have the vertical loads here, we just need the time series, okay? The time series, we just need the dead load time series, so the ramp for the application of the vertical load. And as I told you before, we just have 3 kinds of vertical loads. So the nodal forces in the middle, these forces here on the facets, and this force here on the corners. And we are fine. So this one are the vertical loads. After we have the vertical loads, we can run a static gravity analysis. So open this one and you can see that it is a static analysis, simply a transformation method. Oh, by the way, all the settings in all these analyses are the same. they will just change from static to transient when we are going to do the time history analysis. Okay, so transformation for everyone, a UMF pack sparse solver, and then I'm using the Coulomb Newton, but just for speed. But any other kind of solver will work with this example. This one is a load control analysis, so the total duration is 1, okay, because it is a static analysis. I don't need many steps, just 10 steps are fine. Okay, so after you do this one, don't forget to click on the load constant because we want to keep the vertical load constant, and then we reset the time step to 0. Now in this case, yes, you want the wipe analysis because you are moving from a static analysis to a transient analysis. So you need to click on wipe analysis because based on the OpenSees documentation, if you move from a static to a transient analysis without the wipe analysis, you may have some error under certain circumstances. Okay, so do not forget to keep the wipe analysis, which is, by the way, on by default. Okay, so once we have the gravity analysis done, we can start setting up the dynamic analysis. Okay, so the first thing that we do is to apply the damping. Now for damping, I've been using Rayleigh damping, but only stiffness proportional. There is a reference that I will share with you that explains why in a base isolated system it is better to use a stiffness proportional damping. Okay, so once you have the damping, you need to apply uniform excitations. The uniform excitation is basically going to apply an acceleration to all the nodes that are fixed. Okay, so we want to analyze both a accelerogram in x and y direction, so we need 2 uniform excitations. This one is called acceleration x. So the first thing that you need to do with a uniform excitation is to choose the direction. Now this one will be x, and you need to choose the time series for the acceleration, and this one will be the Kobe acceleration in x. Same thing for the acceleration in y. You just need to choose the dy direction and the time series for the Kobe in y direction. Okay, so once you're done with the uniform excitation, which is basically the loads for our time history analysis, here we created some monitors just because we want to monitor in real time what's going on in our structure. Okay, now they are not mandatory, but they are nice because they allow you to understand what's going on in your model while OpenSees is running. Okay, so the first one is called monitor time versus FZ, which is the vertical reaction, and I use this one to check the uplift because, as you know, I applied a no tension model, and I want to make sure that the vertical reaction never goes down to 0. Okay, because in this case it means that I have an uplift of my structure. How can you check that? Well, you can say, okay, I want to plot in x the pseudo time step, and in y I want to plot the reaction force in the component z in the selection set base nodes. Okay, and as operation, because the default operation is sum, but in this case as operation I want the minimum. Okay, because the vertical reaction will be positive. Okay, so they will act in the positive z direction, and I want to monitor the minimum of them. If one of the minimums goes down or reaches 0, it means that I have an uplift. Here you have some new features in version 2. Basically, this one is a scale factor. By the way, in my model, I am modeling everything in newtons and meters. Okay, but let's say that you want to scale the output of the monitor. For example, I want to plot everything in kilonewton. I can just put a scale factor here, so 1 to the -3. Okay, so that now my abscissa are seconds and my ordinate here are kilonewtons. Okay, so perfect. With this first monitor, I can make sure that I can monitor the vertical reaction, the global vertical reaction, and make sure that there is no uplift. Then I want to monitor the displacement in x and y versus time at the top node here. So once again, we have a monitor, pseudo time step versus displacement in x in the selection set top node, which is just the single node on the top floor. Scale factor 1 because I want to monitor them in meters, which is the basic system that I'm using. Same thing for the y direction, okay? Then I want to plot some displacement versus reaction force at the base nodes, okay? Which basically is also telling me how the isolation system are working. So I have two of them for x and y. Now in this case, I'm plotting a result against another result, okay? So in x, I want the displacement. In the x direction, the selection set will be the top node, okay, top node of the structure. Scale 1 is fine. While in y, I want the reaction force, always in x, but this time I want to compute the reaction forces, of course, at the base nodes, so the one that are fixed, and I want to sum them. Once again, I want the output in kilonewtons, so I scale them by a factor of 1 to the minus 3, okay? So my output will be meters versus kilonewton. Same thing for the y direction, okay? Now let's say you want to understand how your isolation system is moving in the xy plane. You can create a monitor like this one, ux versus uy, and you say that in both x and y direction you want to plot displacement, okay? In the x direction you want to plot the displacement in the x direction, in the y direction in the y, and here you choose the node that you want. Now in my case I was monitoring the top node of the structure, okay? This one is meter versus meter, so I don't need to put any scale factor. That's fine. Okay, so here I finished creating all my monitors. Okay, now I need to, let's say this is the toughest part of my model. After this, I can run the time history analysis, okay? But later on, I would like to run an eigenvalue analysis after the time history analysis, okay? So let me just explain you this. So imagine I don't have these ones and all these ones. So I just do a time history analysis and then an eigenvalue analysis. Now what is going to happen? Well, time history analysis is pretty simple. It's the same as before, but it is just transient. Okay, so transient analysis, transformation, reverse. This is the same. You just need to change the integrator because it was a load control in static analysis. Here we are using an implicit method, the Newmark method. And as I told you, I'm analyzing only 15 seconds. Okay, but if you want to complete the analysis, you can put 40 here. Okay, and of course 4,000 steps here because my samples are 0.01 seconds. Okay, so here load const is not important because I don't have any further analysis after this one. But now if you run the analysis here, your isolation system will go into a nonlinear stage after the analysis, as obvious. And the problem is that I've seen a lot of people doing eigenvalue analysis in OpenSees after a nonlinear analysis. Now this is fine. The problem is that you have to understand what the stiffness matrix means in OpenSees for the elements that you selected. Because basically the stiffness matrix will be used in the eigenvalue analysis, of course, to compute the eigenmodes and eigenfrequencies. Now, what is the problem? If after the time history analysis your model goes into a nonlinear stage, the eigenvalue analysis will call the tangent matrix for every component. Now, the problem with the tangent matrix is that they do not always have a physical meaning, because the tangent matrix has a physical meaning only in linear elastic analysis, because it contains the constants of elasticity of your model. But when you are into a nonlinear range, they just contain a bunch of derivatives, okay? So they can be zero, they can be even negative, if you, for example, if you have softening. So they lose their physical meaning, and so to me it does not make sense to run an eigenvalue analysis onto a nonlinear model, okay? So I did some tricks here to kind of compute an equivalent stiffness for the isolation system and to remove the isolators and put these equivalent linear springs. I will show you later on, but for the moment, let's just nullify the effect of this script. I will explain it to you later on. If I just go here and I put a 0 here, so don't worry, I will explain you the contents of the scripts in a few minutes. But for the moment, I just want to remove this one. So this one will not be applied. And if I run the analysis like it is, it will do an eigenvalue analysis of the elastic fixed base structure. Then it will do a time history analysis. My model will go into a nonlinear stage. And then it will do an eigenvalue analysis on the nonlinear model. And you will see that the results are quite weird here. Okay? And then I will explain you all these other components that I put here to overcome this problem. Okay, so when you are done, you can just run the analysis. It will take just a couple of minutes. In the meanwhile, you can monitor what's going on. So as I said, here we have many monitors. The first one is the vertical reaction versus time. So here we have about 300 kilonewtons, 300 kilometers here, and as a starting point, and then during the analysis it will oscillate, but as you can see, they are never reaching 0 now. Then if you move to the other plots, here you can visualize the displacement in x direction, displacement in y direction, and then you have displacement versus reaction force in x direction. Then you have the same in y. And then you have this last plot here, which is used to track in the x-y plane how the top node is moving. Okay. So let's go back to the isolator here, which makes sense. And let's see how it works. Now we are about at 60% of the analysis. Let's wait a little bit and let's see what happens. %, we are almost done. Okay, so let's go and see the output. Well, here we have all the output on the screen, but as I told you, it has already been saved on the folder, so I can close it. We can go on the folder where we had the file, and here we have the modal properties initial, and if we open it, we can see that we have our first and second period, which are about 0.5 seconds. Okay, they are pretty similar. The second one slightly less than the first one. Okay, but just remember the order of magnitude, 0.5. Then if we go and see the modal participation masses, we see that it reaches an 85% the first mode, then 85% in X, then we have some torsional modes, and finally it reaches the 95%. Okay. If you want to see the eigen modes, you can go on the postprocessor. You can open the results, and in the results here we have 4 stages. The first one has the results for the first eigenvalue analysis. Okay. Then you have the gravity analysis, then you have the time history analysis, and then you have the final eigenvalue analysis. Okay, so let's start by watching the first eigenvalue analysis. So here I choose modes of vibration as color, but also modes of vibration as deformation, and I want to increase my deformation a little bit. Okay, so first mode in Y, and it makes sense compared to the amount of effective mass here, which is in Y. Okay, so second mode is in X. Then we have a torsional mode, sorry, is this one. And then the other minor modes, okay, so pretty standard. Then if we go here to the second analysis, of course we don't have modes of vibration, we just have the displacement. Let's see what's going on. And here this one is too much, so let's put 100. Then you can do an animation. You can see that at the beginning you have just a displacement of the vertical analysis, and then as you move it, okay, the isolation system will start being active, okay? And this is what we want, okay? So it is isolating our system. The problem is that if we go and look at the eigenvalues of the final analysis, so the eigenvalues after the nonlinear analysis, you will see that there is a huge difference between x and y, where we would expect the same period in x and y. So here we have 3.2 seconds in x and 0.7 in y. Then the amount of masses is fine because it is isolated, yes, but why there is this huge difference between x and y, where you would expect the same period in both directions? Well, basically because the eigenvalue analysis here is asking for the tangent matrix, but the tangent matrix into a nonlinear model has not a physical meaning, or not always it has a physical meaning. So sometimes it can give you a problem. Now imagine if I just run the analysis for another second, those values will change. Sometimes they will change a lot. So the problem is that even if OpenSees allows you to do eigenvalue analysis after a nonlinear analysis, you have to understand if it makes sense or not. Now in this case, it does not make any sense to me, okay? So if we go back in STKO preprocessor, I just made a little trick to remove the isolation system and replace them with an equivalent spring that has an equivalent stiffness, okay? And the equivalent stiffness, we will see that will be compared to the equivalent stiffness computed here, okay? So basically when, let me explain you just a little bit how these scripts here that I will explain, how they will work, okay? So basically, this is not opening, but that's fine. Okay, anyway, let me show you. So the first thing that we need, because our final aim now is to take all the isolators here, take them results, okay? I want to know each one of them, what is the force versus displacement, both in x and y. Once I have the force displacement curve, I want to compute the equivalent stiffness, okay? Now for some reason here I cannot use the annotation. Let me see if I can show you using a drawing. Okay, so basically for every isolation system, I'm going to, I will have a graph which is something like this, okay? What I will do is just compute the maximum, or this is displacement versus reaction force. What I'm going to do is just to compute the equivalent stiffness of this graph, okay? So I will reach a maximum displacement in positive direction and negative direction, and I will reach a maximum force in positive and negative direction, okay? Then I grab the maximum, the max one of them, okay? And then I compute the secant stiffness going from the center to the last node of my graph, okay? And this one will give me an approximation of the equivalent stiffness of my isolator, okay? Once I compute this one, and this one will everything will be done in TCOL. Once I compute those values, I will basically use a script that removes the isolators and replace them with a linear spring with that specified stiffness, okay? And after that, I will run the eigenvalue analysis. So how can you do this stuff here? Well, first of all, we will take advantage of the custom script that we have in STKO, so that you can write a TCOL script that allows you to do whatever you want, basically. So the first thing that I need is to create an isolator region, okay, which is a region command in OpenSees that contains all the element tags for the isolators. How can you do that? Well, you can go under modal, miscellaneous command, and you choose region. When you choose the region, you need to select the selection sets that contain the isolators, okay, so this one. Then you have to choose the region type. It can be node or elements, but of course in this case I want to know the tags of the elements, so I choose element. And then I use this new feature that we have in STKO version 2. I want to write the contents of these elements, so all the IDs, onto a list, okay? And this list will be called in TCOL isolators, okay? So just to show you how it will be written, if I go under the analysis steps, and let me search for isolators, just to show you, okay? So this one is the region command. The region command will produce a region, but also a list in TCOL containing the IDs of the elements. Okay, this is useful, for example, if you want to create a custom script later on that needs to know what are the elements in the isolation system. Okay, now basically you have two options here. You can either go in STKO, you can go under the mesh, you can switch on the labels, okay, and go here and see the element ID one by one, but it is quite tedious. Otherwise, you can use this kind of command, which is more automatic, okay? So you just say, I want to write their ID on a list, okay? And it will be updated automatically by STKO. So, for example, you redo your mesh, the mesh numbering will change, and this one will be updated accordingly, okay? So up to here, this one will produce this script. And this is what we really want, actually. Okay, so the next step will be to define some specific recorders for the isolators, and let me show you how it works. So this one instead is a standard TCOL commands. Okay, so if you remember, before I told you that when you create the interaction for the isolation system, you have to make sure that it is created from bottom to top. Okay, so the bottom nodes are the master nodes, so the first node of the link, and the top nodes are the second nodes. Why? Because later on we will be using the script here, and we assume that the nodes, the first node of the element is the node where we can get the reaction, so the base node, and the second node of the element is the node where we can get the displacement, so the top node of the isolator. So how can you do that? So you can allocate two lists in TCOL, two empty lists, and then you say for each element ID in the isolators list, which is the list I told you before, this one. For every element here, I can get the node tags of this element just by using the OpenSees command lnodes. So there is an OpenSees command called lnodes where you pass the element tag, and it will give you a list containing the tags of the node, okay, that are shared by that element, okay. Now, since this is a list, I know that this element is a two-node element, so this list has a length of 2. Okay, so if I want to access the first node, I can use the list index command of the node list at position 0. It will give me the first, the base node, the node where I can get the forces, the reactions, and the same thing with the ID 1. I can get the top node, okay, which is the node where I want to monitor the displacement. And then I append this node and this node here onto this list. Okay, so after this loop, basically, I have two lists whose length is equal to the number of isolators. Okay, so for each isolator, I have its top node here and its bottom node here. Okay, so for isolator 1, it is here, for isolator 2, it is here, and each one for every column. Okay, so once I have this list, I can create a recorder, a node recorder, okay, for all the nodes in this list, and then basically I create 4 recorders, okay? A recorder for the UX displacement in the X direction, and a recorder for the force in X direction, and the same thing for Y direction, okay? So how can you do that? Basically, you can use the recorder command, the nodal recorder command, then you say that you want to print it on a file, and the file will be ISO data UX FX UI FY. Then you want to specify the nodes one by one, and you can use this TCOL syntax. So since this one is a list, you need to expand list here, okay? This one is a specific TCOL command, otherwise OpenSees will not understand that you have many nodes, okay? So once you have done that, you can specify the degree of freedom. So the first two are X direction, so 1, and the other two are Y direction, so 2. And here one displacement, and here the reaction, and same thing here, the displacement and reaction. Okay, now I'm pretty sure you've always seen the recorder command, but you have never seen this kind of operation here. Because if the recorder command in OpenSees actually gives you an output, okay? Basically, no one uses it because it is never used. But in this case, I need to grab the result of this command. And the result of this command will be the ID, so the tag of this recorder. I need it because later on I need to remove those recorders, okay? So if you want to keep track of the ID of a recorder, you can simply enclose the recorder command into a square bracket list, square brackets here, and the output will be the ID of that recorder, okay? So with this script, basically, I'm creating 4 files for the recorders, which are this one, for example, isolation UX, that has 1 row for every time step. So it will be, in my case, 1,500 rows, okay? And 1 column for every isolator, okay? So this one will be the displacement X for the first isolator, second isolator, third isolator, and so on, okay? So let me switch off this one, and also those. Okay, so here I define my recorders. Now, when I define the recorders, I run the time history analysis as before, and then soon after the time history analysis, I need to do some post-processing, okay? I need to take those recorders, and from them, I need to compute the equivalent stiffness. So the next command, which is also a custom command, is called post-process isolator recorders. And that's why I needed those to keep track of those tags, because before post-processing them, I need to remove those recorders. Why? Because if you don't remove them, you will not be able to get the data from that file until OpenSees closes, okay? But I need to do some operation before OpenSees closes, okay? So to get the data while OpenSees is still open, you need to close the recorders, okay? So I remove the recorders because I don't need them anymore. Once they are closed, I can get the data from those files, okay? So the first thing that I do is to open a file, okay? One for each one of them in read-only mode, okay? That's why I put an arc here, okay? So these ones are the handle for the 4 files. Then I get the data from those files. And what is this syntax? So the read command reads the entire content of a file, okay? So basically it is a huge string. Then I want to split them using the new line character, okay? So basically after this operation here, I have a list of strings, okay? 1 for each row. Now since in OpenSees the last row is empty, and to avoid a crash later on, I need to use this command, which is basically taking this list and removing any row that is empty, okay? So the last one, basically. Now, after this operation, each one of those data here will contain a list of strings, okay? 1 string for each time step, okay? Once I get all the data, I can safely close the file handles because now my data is on memory. Okay, I don't need to keep them open anymore. Now I can get some numbering here. The number of isolators will be equal to the length of the isolator list, so the same list I've used before. And the number of time step is equal to the length of one of those files, okay, because they are the same. Okay, so for example, here I took the length from data UX, but the same length will be equal for the other files. So now I have the number of isolators and the number of time steps. And then, as I told you before, I need to compute the maximum displacement and actually the absolute maximum displacement and the absolute maximum force for each isolator, okay? And this is what I'm going to do here. Okay, so I set up the maximum here, set as 0, then I do a loop on all time steps, I get the data from each row, then I split this data and I get the data for each column, okay? And then I compute the maximum, the absolute maximum, and I store them here, okay? After this computation, once I have the maximum displacement for X and Y and the maximum forces for X and Y, For each isolator, I can compute the equivalent stiffnesses, okay? After this operation here, I have two lists. One containing the equivalent stiffness in X, and one for each isolator, and the same thing in Y, okay? Once this is done, I can go on with the script, okay? That before was switched off, now I switch it on, so you can see the difference, okay? Now, before explaining you how it works, I want to show you something in the postprocessor, because now I can understand that it is quite difficult to understand how it works just by looking at the code. So I took advantage of the Python scripting in STKO to show you exactly what that script is doing, okay? So that script is basically taking these four files, is reading them, is computing the X and Y maximum displacements, and then it is computing the equivalent stiffness. So let's see how it works. Here I'm also going to plot it, and this is one of the ways, of the many ways you can use the Python API inside STKO. So if I run this one, I have these two plots here. This one is basically plotting all the displacement versus force, one for each isolator. So as you can see, there are many of them overlapping here in X and here in Y. And as you can see, we are reaching a displacement of about 19 millimeters in each direction, okay? And this is basically what I was showing you here for just one single isolator. So once I have this this graph, I need to compute the bounds, okay? So maximum displacement, maximum forces, and this is what the script is doing. Once I do that, I compute the stiffnesses. Now, as you can see, I can put the stiffness here on a histogram, and you can see that I basically have three groups of stiffnesses, okay? Some of them being around 500,000 newtons, some of them being around 300, and some of them about 200, okay? We have these three groups because we are using the same isolator, but as I told you before, we have three kinds of vertical reaction, okay? So we have the largest vertical reaction in the central nodes, a medium reaction on the facade node, and the smallest reaction on the corner node. That's why we have three groups of stiffness. So this is proving that our model was working, and the stiffness that we computed here are actually working, okay? So basically, this is what's going on in that script. Now, back to the TCOL. So this one is not necessary, as I told you. It's not necessary for the computation. It's just to give you an idea of what's going on visually, okay? But the computation that I do here in Python is the same computation that I'm doing here in TCOL. Okay, so you have a kind of check of what's going on. So as I told you, here I have all the graphs, and then I compute the stiffnesses, okay, just by taking the maximum force in X divided by the maximum displacement in X, and then the maximum force in Y divided by the maximum displacement in Y. And this is what I'm basically calculating, is the secant stiffness, which is the definition for the equivalent stiffness for the isolators. Okay, so once I have them, I run this script here. I enclosed it into an if statement just to show you the difference between not using it or using it. Okay, so before I was not using it, so my eigenvalue analysis was performed onto the nonlinear model. Now in this case, I'm basically substituting the isolators with equivalent elastic stiffness using the reduced stiffness, the one that I calculated here. So how can you do that? Well, first you need to create some offsets for the new materials, because I'm going to create new materials, one for every, actually two, one in X and one in Y, one of them for each isolator, okay, because basically each isolator has a different equivalent stiffness. And then I do for every isolator, okay, for J that goes from 0 to the number of isolators, I take the isolator tag, okay, so the tag of the element that I want to remove. Then I take the first node, the base node, and the top node, and then I take the stiffness, the equivalent stiffness I computed in X and Y. Okay, so once I have this data, I can remove the element from OpenSees, and you can simply use the remove command followed by the element keyword, because in OpenSees the remove command is used to remove a lot of things. Okay, one of them being the element. So if you want to remove an element, you write remove element and then the element tag, okay, which is this one, okay, the tag of the isolator. So I remove the element, and then I create the uniaxial material in X and Y for the for my equivalent spring. Okay, so I say the material in X will be an offset here plus the isolation tag. So it's just a number that does not overlap with the previous numbers here. Then I create a tag for the material in Y, and then I create two uniaxial material which are elastic with this new tag and using the new stiffness that I computed in X and Y. And then I create a zero length element. For the zero length element, I can use the same tag of the previous isolator because here I remove them. Okay, so if this element has been removed, I can add another element with the same tag, and it is not going to give an error because the previous element with the same tag has already been removed. Okay, so basically I remove the isolator system and I add an equivalent spring connecting the same nodes, okay, with three materials, the one in X and Y, which are specific to this spring. And the material in Z is actually the material number 10, which is the same that I used for the isolator, okay? So all of them have the same stiffness in Z. And of course, I want to apply these three materials in the three directions, X, Y, Z. After I've done all this change, I call domain change because now my model has changed. Actually, me, the user, has changed the model. So I need to tell OpenSees that something has changed in the model, and you can use the domain change command. Okay. So once you have done this, make sure you have the one here. So this script is running. If you run the analysis now and you perform the eigenvalue analysis, you will see that now the results are different. Okay. And if you remember, before we had a final model properties that has a period of 3.2 here in X and 0.7 in Y. This is quite strange because I was expecting the same value, okay, which is about 3 seconds. And it is about 3 seconds because here also the computed value is about 2.7 from the computation of the properties of the single isolator. Okay, so make sure to have one here and we can run the analysis again. Let me double check it. I have one here, okay, and I can run it. Now this is going to overlap the previous results. So just remember that our periods were 3.2 and 0.7. Now just wait a couple of minutes and then we are done. Now, of course, the result of the nonlinear analysis is not going to change because the only thing that I'm changing is the way it does the final eigenvalue analysis, okay? So everything is happening here is actually the same that I've seen before, okay? See, 70%, we're almost done. Yeah, almost 2 minutes. %. Okay, so this is finished. Let's close it and let me go here and I open the final one. Okay, so let's see now you can see that these two periods are equal, but almost equal, 3 seconds. And also the modal participation masses, now they make more sense. It is 99% in X than in Y, okay? And the torsional one is only on the fourth one, okay? But the most important thing is that now it makes sense, because now the stiffness of my model was actually an elastic stiffness, okay? While before it was the tangent stiffness of a nonlinear model. So the problem is that the tangent stiffness, it is just a mathematical number. It's not something physical unless the analysis is linear. So the bottom line here is just OpenSees allows you to do an eigenvalue analysis when your model has gone into a nonlinear stage. But pay attention, because you need to understand first the element, what kind of stiffness it produces, because not every element or not every material is implemented in such a way that it gives you an exact tangent stiffness. Sometimes they just give you a secant stiffness, sometimes they can give you an initial stiffness. It does not change the results, but if you use that stiffness for the eigenvalue analysis, it is going to change the result, okay? So always pay attention to that. In my opinion, I always do an eigenvalue analysis on a linear system. And if I have a situation like this, instead of running the eigenvalue analysis onto the nonlinear model, you can just compute an equivalent linear model, like I've done in this example. So I just take the equivalent stiffness of my isolator here, and then like I did in this sketch here, you substitute your nonlinear model with an equivalent linear model that describes the nonlinear behavior at that point of the analysis, and you run the eigenvalue analysis. Okay. Okay, I can close this one. Now, just to make sure we can go in the postprocessor here. We can reload it, but the analysis is not going to change, as I told you. It's just the only thing that has changed is the fourth step. And if you want to see the modes of vibration, just to see how they are now that the system is isolated. Okay, so the first mode is like this one. Let me increase it. Okay, so it makes sense. Isolated here, second mode in Y, and then you have torsional mode at the end. Okay, it makes perfectly sense. So we are done with this webinar. So I think, yeah, it's quite interesting for people that are using OpenSees and STKO on a more complex level, because now I told you how you can use scripting environment either in OpenSees or in STKO to customize the way your analysis work. Okay, so most of the people just use the standard commands that are provided by the software. But when a software allows you to add things through a scripting interface, you can do many more things, okay? Both in terms of analysis, as I did here with Coulomb, and in terms of post-processing or even pre-processing, as I've done here in STKO. So I know it can be difficult at the beginning, but in every new webinar in this year, we will be focusing on using the Python API, okay? Because it will give you a huge advantage. Okay, so we are done, and we have some minutes for questions if you have any. So if you have any question, please, you can write it on the chat. Just a second, we have some problems here stopping the sharing. Oh, Zoom is going crazy. Just a second. finally. Just give me a second, there is something wrong with Zoom here. I don't know why it is not working. I cannot stop sharing. Do you see my screen? Just a second. Okay, so just a second, I'm going to exit from Zoom and enter again because it is going. Io non riesco a uscire da qua. Okay, so I move to another. Sorry, no, it's on. Okay, here we are. Sorry, I moved on another computer. Yeah, because Zoom was crashing on the other side. So I apologize for that. Do you have any question? Yeah. Okay, here I can see the questions. Okay. Can you tell me more about the initial stiffness, please? Okay, so the problem with the eigenvalue analysis is that the eigenvalue analysis uses the tangent stiffness. Okay, in OpenSees, every element is able to give you three kinds of stiffnesses. Okay, the tangent one, the committed one, and the initial one. The problem is that the initial stiffness is constant for every element, which is the linear elastic one, and that would be the one that you want to use in eigenvalue analysis. The problem is that the eigenvalue analysis in OpenSees calls the tangent stiffness, and the tangent stiffness is just contains a bunch of derivatives, the derivatives used by the Newton method to iterate, but they do not have any physical meaning. That's why if you do an eigenvalue analysis with the tangent stiffness, the results are not reliable because you don't know that component in the tangent stiffness, what kind of meaning it has, okay? And it also depends on how the element computes the tangent stiffness, because sometimes they don't even compute the real tangent, they compute some kind of approximation. So do not rely on the eigenvalue analysis on a nonlinear model. If you want to do it, you can do as I did in this example, where you basically remove the nonlinear model and you use an equivalent one. So second question, does the model of the friction pendulum bearing assume small deformation? It means the normal load is similar to the weight force. Actually, I've seen in the code, actually, but I need to test it a little bit more, that it also has P delta effects. They can be included. But actually, I need to look into the code because I couldn't see a good documentation on that. Then another question, can we use a series model between the friction pendulum bearing and a contact model such as Hertz model? You can do it, but you have to do it not with a series material, if you refer to that, because the series material in OpenSees, it works only for uniaxial materials. So if you want to do that, you have to create two elements in series, okay? But the problem is that you cannot do it very easily. So probably
what you can do is to try to use the Hertz model, which is a uniaxial model, on the Z component, where basically I used the elastic no tension. Okay, so in that case, it can be done. And then you can use a series model. Another question, if we were able to create this kind of model using the free version, probably something smaller, because the free version has limitation on the number of elements. Okay. Okay, there is just an answer for this. Yes, all the features are included, just limited. Okay. How many elements can we use? It will be on the website tomorrow, but basically you have a limited number on the number of elements, 20 elements, 20 line elements, 200, 150 shell elements, and 200 solid elements. Okay, so depending on the kind of element type you want to use. So next question by Chiara, what's the domain change command used for? Okay, so the domain change command is used to inform OpenSees, to notify OpenSees that something has changed in the domain. The domain is basically the collection of nodes, elements, loads, boundary condition. Now, typically OpenSees does it internally when, for example, you switch from an analysis settings to another, okay? And for every domain change in the MPCO recorder, you see a different model stage, okay? So OpenSees takes care of calling the domain change command internally, but only when you do certain operation. For example, when you remove elements or you add new elements or you remove boundary condition, it does not always call domain change. So if you want to make sure and you know that you made a change in a model, like I did, for example, removing element and adding other elements, always call the domain change. It will basically make sure that all the system of equation are reshaped, okay, to match the new number of nodes or the new number of elements, okay? So whenever you do a change in the model, call domain change. Another question, how do you fix the rotational stiffness of friction pendulum isolators? I do not understand what you mean by fix the rotational stiffness, but if you mean how do you include the rotational stiffness, you can do it. As I told you, I was using a zero stiffness for rotational friction, for rotational components of the friction pendulum. But if you want, you can add any kind of stiffness or actually any kind of material model for rotational component, okay? Because in OpenSees, you can just add a uniaxial model. So typically it will be an elastic model and you put an equivalent elastic stiffness that you want. In my case, it was zero. You may use any kind of stiffness that you want to compute or even a nonlinear model. But in any case, you define a uniaxial material and you assign it to the torsional and bending components. If this is what you meant, okay? Is there any other question? Is it possible to add a hook element in series with a friction pendulum isolator element? Yes, well, basically, we have to make it clear. If you want to put something in series, okay, with an element, because the friction pendulum is an element, it is not possible to apply two elements in series using some automatic command. You just need to create two elements shared by the same node, and of course they will act in series. If you refer to series as if you're referring to the series material model, that can only be used with uniaxial models, okay? And the friction pendulum isolator is not a uniaxial material model; it is an element, okay? So of course you can do it, but not using the series material model, unless you want to create a series combination of two stiffnesses in either the normal, so the vertical, or rotational directions, okay? But if you want to do something in the shear direction X and Y, you are not allowed to do so because the friction pendulum is not an element, but it is not a material model, but it is an element. Okay, is it clear? If there are some other questions, we have another couple of minutes. Okay. So I think we are done. And I would like to thank everyone for taking part to this new webinar. And once again, by tomorrow, you will be able to download version 2 of STKO and all the contents for this webinar and the previous webinar on response spectrum, okay? Because we were waiting for the new version to be released in order to update the file contents for the response spectrum analysis. So by tomorrow, you will be able to download all of them. So thank you, everyone.